Brian Cox, a renowned physicist and science communicator, often discusses black holes as key to understanding the deeper mysteries of the universe. He suggests that black holes could provide insights into fundamental aspects of physics, including gravity, quantum mechanics, and the nature of space and time. One of the main ideas is that black holes challenge our current understanding of physics, particularly when it comes to reconciling Einstein's general theory of relativity, which describes gravity and large-scale structures, with quantum mechanics, which explains the behavior of particles on the smallest scales. At the heart of this conflict is the event horizon of a black hole. Beyond this boundary, not even light can escape, and everything we know about physics breaks down. Cox has emphasized that studying black holes, especially their role in producing phenomena like Hawking radiation, the theoretical radiation emitted by black holes, might help us develop a theory of quantum gravity, which is one of the biggest unanswered questions in modern physics. Black holes could also provide clues about the early universe, as they represent extreme conditions similar to those that might have existed at the time of the Big Bang. Moreover, Cox has speculated that black holes could hold answers about the information paradox. What happens to the information about matter that falls into a black hole? Resolving this paradox could lead to new discoveries about the fundamental nature of the universe. In short, Brian Cox believes that unlocking the secrets of black holes could open up new avenues for understanding the universe's most profound. Brian Cox, a highly respected physicist, broadcaster, and professor of particle physics, has captivated audiences with his ability to explain complex scientific ideas in a clear and accessible manner. One of the topics that he is most passionate about is black holes and how studying them could potentially unlock some of the greatest mysteries of the universe. Black holes are not just regions of space where gravity is so strong that not even light can escape. They are also extraordinary laboratories for understanding the laws of physics in extreme conditions. According to Cox and many other leading physicists, studying black holes could provide key insights into fundamental problems in physics, including the nature of space and time, the connection between quantum mechanics and general relativity, and the origins of the universe. The nature of black holes. Black holes are among the most mysterious and fascinating objects in the universe. They form when a massive star collapses under its own gravity at the end of its life cycle. The gravitational pull becomes so strong that everything, including light, is pulled into a singularity, a point where density is infinite, and the known laws of physics break down. Surrounding the singularity is the event horizon, which marks the point of no return for anything that gets too close. Once something crosses the event horizon, it can no longer escape the black hole's gravitational grip. While black holes were once considered purely theoretical objects, their existence is now well established. Over the past few decades, astronomers have found overwhelming evidence for the presence of black holes, ranging from the supermassive black holes that reside at the centers of most galaxies to the smaller black holes formed by the collapse of massive stars. In 2019, the first direct image of a black hole was captured by the Event Horizon Telescope, providing a stunning visual confirmation of a supermassive black hole in the galaxy M87. Despite these discoveries, black holes remain deeply mysterious. One of the biggest challenges in understanding black holes is that they push our current theories of physics to their limits. According to Einstein's theory of general relativity, which describes how gravity works on large scales, a black hole is a perfectly smooth, featureless object. However, when we try to understand what happens near a black hole using the laws of quantum mechanics, which govern the behavior of particles on the smallest scales, the two theories come into conflict. This suggests that our understanding of the universe is incomplete, and that black holes could hold the key to a deeper, more fundamental theory of nature. The problem of combining general relativity and quantum mechanics. One of the most significant challenges in modern physics is the problem of combining general relativity and quantum mechanics into a single, unified theory. General relativity describes how gravity works on large scales, explaining the motion of planets, stars, and galaxies. Quantum mechanics, on the other hand, explains the behavior of particles on the smallest scales, such as electrons, photons, and quarks. Both theories have been remarkably successful in their respective domains, but they are fundamentally incompatible with each other. In most situations, this incompatibility doesn't cause problems, because the effects of quantum mechanics are usually too small to be noticed in the presence of strong gravitational fields. However, black holes are unique because they involve both extreme gravity and quantum effects, The singularity at the center of a black hole is a region of infinite density, where general relativity predicts that space and time break down. At the same time, quantum mechanics suggests that particles should behave in a certain way near the event horizon. This creates a paradox, as the two theories give different predictions about what happens near a black hole. According to Cox, solving this paradox is one of the most important problems in physics today. He argues that studying black holes could help us develop a theory of quantum gravity, which would unify general relativity and quantum mechanics into a single framework. Such a theory would not only explain what happens inside black holes, but could also shed light on other deep mysteries, such as the nature of space and time and the origin of the universe. Hawking radiation and the information paradox. One of the most famous ideas related to black holes comes from the physicist Stephen Hawking, who proposed that black holes are not entirely black after all. In 1974, Hawking showed that black holes should emit a faint form of radiation, now known as Hawking radiation. This radiation is produced by quantum effects near the event horizon and causes the black hole to slowly lose mass over time. Eventually, if the black hole emits enough Hawking radiation, it will shrink and disappear entirely. While Hawking's discovery was a major breakthrough, it also created a new puzzle, known as the information paradox. According to the laws of quantum mechanics, information about the state of a physical system should never be lost. However, if a black hole evaporates completely due to Hawking radiation, it seems that all of the information about the particles that fell into the black hole would be lost forever. This contradicts the principles of quantum mechanics, which state that information must be conserved. The information paradox has puzzled physicists for decades, and it remains one of the biggest unsolved problems in theoretical physics. Cox and many other scientists believe that resolving this paradox could lead to major breakthroughs in our understanding of the universe. Some researchers have proposed that the information is somehow encoded in the Hawking radiation itself, while others suggest that the information might be stored on the event horizon in the form of a hologram. These ideas are still speculative, but they offer tantalizing hints of a deeper theory that could reconcile the contradictions between general relativity and quantum mechanics. Black holes and the early universe. Black holes are not only important for understanding quantum gravity and the nature of information. They could also provide clues about the origins of the universe. According to the Big Bang theory, the universe began as a hot, dense state and has been expanding ever since. However, the conditions in the early universe were so extreme that our current theories of physics are unable to fully explain what happened in the first few moments after the Big Bang. Cox has suggested that black holes could offer a unique window into these early moments of the universe. The conditions near a black hole singularity are thought to be similar to those that existed in the very early universe, where both quantum effects and gravity were extremely important. By studying black holes, scientists might be able to gain new insights into how the universe evolved and what happened in its earliest moments. Moreover, some researchers have proposed that black holes could have played a significant role in the formation of the universe's large-scale structure. For example, the supermassive black holes found at the centers of galaxies might have helped shape the formation and evolution of galaxies themselves. Understanding the relationship between black holes and galaxy formation could provide important clues about how the universe evolved from a uniform state after the Big Bang to the complex and structured cosmos we see today. Black holes and the nature of space and time. One of the most profound questions that black holes raise is about the nature of space and time itself. According to Einstein's theory of general relativity, space and time are not fixed and absolute. Instead, they are dynamic entities that can be warped and stretched by the presence of matter and energy. Near a black hole, the warping of space and time becomes so extreme that time appears to slow down for an observer approaching the event horizon. This warping of space and time leads to some strange and counterintuitive effects. For example, an observer falling into a black hole would appear to slow down and freeze at the event horizon from the perspective of a distant observer. However, from the perspective of the person falling in, time would continue normally, and they would eventually reach the singularity. These effects challenge our everyday understanding of space and time and suggest that black holes might hold the key to a deeper understanding of these concepts. Cox has emphasized that studying black holes could lead to new insights into the nature of space and time. In particular, black holes might provide clues about how space and time emerge from more fundamental principles. Some theories of quantum gravity, such as string theory and loop quantum gravity, suggest that space and time are not fundamental entities but instead arise from more basic building blocks. Black holes could provide a way to test these ideas and gain a deeper understanding of the fabric of the universe. Black holes and the future of physics. For Brian Cox, black holes represent one of the most exciting and important frontiers in physics. He argues that studying black holes could help us answer some of the most fundamental questions about the universe, including the nature of space and time, the relationship between quantum mechanics and gravity, and the origins of the cosmos. By unlocking the secrets of black holes, we could potentially discover new laws of physics that go beyond our current understanding. In recent years, there has been significant progress in black hole research. The detection of gravitational waves from colliding black holes by the LIGO and Virgo observatories has opened up a new way of studying these objects, allowing scientists to observe their behavior in unprecedented detail. Additionally, the Event Horizon Telescope's image of the black hole in M87 has provided new insights into the structure of black holes and the nature of their event horizons. Despite these advances, there is still much to learn. Many of the deepest mysteries about black holes remain unsolved, and physicists are continuing to develop new theories and experiments to probe these enigmatic objects. As Cox and other researchers continue to explore the mysteries of black holes, they are not only expanding our knowledge of these extraordinary objects but also pushing the boundaries of our understanding of the universe itself. In conclusion, Brian Cox's views on black holes highlight their potential to revolutionize our understanding of the universe. Black holes challenge our current theories of physics, offering a unique laboratory for studying the interplay between general relativity and quantum mechanics. They also raise profound questions about the nature of space, time, and information, and could provide key insights into the origins and evolution of the cosmos. As physicists continue to study black holes, they may unlock some of the greatest mysteries of the universe and open up